Alright, welcome to another AQA level chemistry video. Um, the last video I did was on pretty much the structure and reactivity of benzene or aromatic compounds, but realistically here we're talking about benzene. Structure and reactivity of aromatic compounds. I have brushed on this topic of reactivity. By reactivity I mean the way it reacts and its reactions, but I was talking mostly about the structure in the last video. So this video here is going to be about the reactions of benzene, in which case I already touched from the previous video, but it's an electrophilic substitution reaction. If you want to go watch the previous video about where I talk about the structure of benzene, how it keeps its structure, I actually answered an exam question in that previous video. So if you want to go check out that video, it literally is the previous video, but I probably will leave a link in the description. If I forget, let me know. Yeah, so I'm going to start the video now and go straight on to that video. So, electrophilic substitution of benzene, right? So, reaction of benzene rings tend to retain the stable ring of delocalized electrons, and that's that stability of that stable ring of delocalized electrons. That's the we call that aromaticity, as said in the previous video. But this is possible in electrophilic substitution when an electrophile replaces a hydrogen on benzene. So electrophilic substitution is the best way instead of addition, because remember in addition reactions you're losing that double bond. You lose that double bond. You usually form an alcohol, but more importantly, if you lose that double bond, then you're no longer maintaining aromaticity. Because you lose the bond, there's one less double bond to alternate for resonance, and therefore aromaticity is not maintained, and therefore it's not a stable. We don't have benzene anymore. It's not the typical benzene that we know. Instead it'll be something else. So the best way and we want to maintain the structure of benzene. Benzene likes to keep its structures very stable. I already talked about why it is so, but electrophilic substitution maintains aromaticity. In case you get any question that's asking about that, it's because it does it because it maintains aromaticity. You might get a question that asks that, so if you ever get that, that's the reason why. So, electrophilic substitution. So benzene rings are electron rich, or I like to use the word electron dense, and so they attract electrophiles. So in itself, benzenes are nucleophiles. If it attracts electrophiles, it's nucleophilic. So electrophilic substitution reactions can be used to introduce halogens, alkyl, acyl, and nitro groups to the benzene ring, and these reactions often require Lewis acid catalyst, AlCl3 and FeBr3. So there's two main three really types of electrophilic substitution reactions that go with benzene. One is chlorination, one is nitration, and another one is called the Friedel-Crafts acylation. The Friedel-Crafts acylation one is the one that usually requires the Lewis acid catalyst, and I'll go through an example of that. Why there's two reactions that you need to know. It's usually with AlCl3. There's two reactions that you need to know that actually AlCl3 is used, and you're showing that it's a catalyst where it's used to form, where AlCl3 forms an intermediate, and then at the end of the reaction it reforms AlCl3. So I'll kind of go through what the basics of electrophilic substitution. Again, I kind of went through this in my previous video, but I'm gonna go over it again just quickly here. So it's just remember the benzene is the nucleophile here, and it's going from the remember the arrow always goes from the lone pair of electrons in this case, or in this case the valence electrons. It's always going from the electrons to the electrophile, and since the benzene is the nucleophile here, it goes from the ring. We know it's from the bonds, but remember we said in benzene the double bonds alternate quite a lot. So you can use the Kekule version of benzene. I prefer to use the ring because it's a better way of representing benzene, and it usually is less complicated, very easy to do. So yeah, I'd represent it like a ring. So we're going from the ring here, which represents the electrons in benzene, to the electrophile, and then the next intermediate forms an intermediate with a positive charge. Overall, we represent it by a positive charge in the center of the ring, and this ring is 2/3 the way full. you can do it as a 3/4, that's fine. But they like to show, in the mark scheme actually specifically says anywhere between 2/3 and 3/4, just showing that you understand that one of the bonds has been broken, and it's formed this intermediate here. And it also, that is now it's positively charged because it's lost electrons. And also to maintain that aromaticity now, it needs to gain electrons. How it's going to do that? It can't do this, right? It can't. It's probably that's probably a polar bond, and it doesn't really want to do that. I mean, it could do that. It prefers this non-polar bond, easier to break, right? Non-polar bond. It prefers this bond here. Why? Well, if I just broke this bond here, but I don't want to muzzle you too much up. Everything I've said apart from that non-polar part, reject that, because I want to make sure that I say this accurately here. But this bond here, if I just broke that, we'll just end up with this again, which is pretty much nothing. What will actually happen is that this hydrogen would be a better leaving group. You form H+. These electrons would then fall into the benzene ring to reform that delocalized pi system, and now you have a electrophilic or electrophile that's now bonded to benzene. And now this is good for, like, for example, this could be applied to that is pretty much how electrophilic substitution works. This could be nitration, chlorination, or Friedel-Crafts acylation, but this is just the general mechanism. So, right, so the initial attack is by the electrophile on the electron-dense benzene ring. The attack on the electrophile breaks the delocalized electron system and forms a positively charged intermediate, which has lost its aromaticity, which is less stable. A hydrogen ion or H+ ion or proton is then removed from the intermediate to regain the aromaticity. And it'll be easy to understand the mechanism as I've already kind of gone through that here, I've kind of jumped ahead here. But yeah, now you kind of get the mechanism, the general mechanism. I went through that in the previous video, but now you get it. So I'm going to go through the first two. So the first thing I'm going to go through here is chlorination and nitration. So there's two specific examples of electrophilic substitution of benzene in chlorination and nitration. And I'll study. We'll kind of study nitration in more depth here. Yeah, I'm gonna go through here. So chlorination, right? So one chlorine atom substitutes a hydrogen atom. This is carried out by electrophilic substitution mechanism, similar to the nitration mechanism. So this is pretty much this, but with CO2. You'll usually separate the chlorine out. I mean, you have the AlCl3 catalyst, but it could easily work out with the mechanism with chlorination and nitration are very similar. The CO2 requires an AL. It's kind of similar with you use the same catalyst as AlCl3 like you do Friedel-Crafts, but ideally the mechanism in itself, you get a Cl+ here, and then that'll be the electrophile here. But yeah, it's pretty much similar to that, so I'm not going to really go over that. So one chlorine atom substitutes a hydrogen atom. Sorry, I've already kind of gone through that. Sorry, nitration. In nitration, the electrophile is NO2+. We call that a nitronium ion, and this will substitute in for a hydrogen atom. The reagents, now this is quite important, right? So this is the one that comes up in the exams. This is why I've kind of specified this one over the chlorination, because chlorination doesn't really come up in exams, and if it does, it's very simple. It's very simple. Just imagine that E+ is just Cl+, and then the AlCl3 part I'll go through later on in Friedel-Crafts, so don't worry about that. But in terms of the CO2 part, the chlorination part, very similar to that. But nitration one is also very easy, not difficult to do, similar to the one up above, but this one comes up in exams because it includes reagents that you would use. There's reagents that you need to use to actually form the nitronium ion, to form the electrophile. And it's very easy, and it requires you to understand, or it requires you to know an equation. You can balance it out really if you're doing it for the first time, but if you've done it multiple times, like I have in the exam, because it always comes up and it's always the same one, you just know it off by heart. But anyway, the most important part here, the reagents and conditions are, so first of all, you need concentrated nitric acid. It's very important that you say concentrated nitric acid, because they will lose. It's like this, so you get like, I think 3 marks, maybe 4 marks, something like that, when it comes to the 50 degrees part. I don't usually see. It's usually these two here, but they usually say concentrated nitric acid and concentrated H2SO4 catalyst. The H2SO4 is actually a catalyst. You don't need to show it being reformed. Like I'll explain why, but most importantly, when you're saying it, you get 2 marks or maybe 3 marks. It'll probably be 3 marks, 2 marks for saying nitric acid and H2SO4 catalyst, and then another mark for mentioning that they're both concentrated. It has to be concentrated for this reaction. That's how it will be done. It won't be done. It won't be done if it's a dilute solution. So very important that you say, if you want to get the maximum marks for just saying what the reagents and the conditions are. If it's conditions, I guess the 50-degree part, but I know conditions would be concentrated. Yeah. So reagents and conditions, concentrated nitric acid, concentrated sulfuric acid catalyst, and then I'll show you how the nitronium ion is formed. So the nitronium ion is formed from the reaction. So it's nitric acid, 1 nitric acid plus 2 H2SO4. It's a reverse reaction to form the nitronium ion NO2 plus 2 HSO4 minus plus H3O plus, right? And thing itself, that's really difficult to remember. Just it's very easy to understand that. Look, you're forming. You know you're gonna form an NO2 plus. You know it's gonna be. You know that this is going to be well, that is one of your. You know that this is one of your electrophiles that's going to be used for your mechanism, right? So you already know that this is going to be here. You already know that that's there. So then the only extra thing that's going to be there is H3O plus, right? Because NO2 plus is already gone, and you know you're going to lose a H2SO4. So you have it just left with, and the charges need to be balanced on these. So you could do, if you really struggle on questions like this, you could do two ionic equations if that helps you out a little bit more. Can I do one? Should I do one? The ionic equation is slightly different to the actual equation. The actual equation, I mean, the H3O plus, I don't really see that as in the ionic equation. It usually be water and then separate out. And the reason why okay, so I'm kind of jumping the gun here, right? If it's in the ionic equation, it'd probably be H2O plus H plus. But usually in acids, when we say H3O plus, because that's how we usually see them as. But they would allow you to say H2O and H plus because if you decided to do 2 ionic equations, right, and then try to make them together, which is perfectly fine. It's what you should do. I'd suggest doing it if they ever asked you to do an ionic equation like that. Yeah, I'd suggest doing that. But if this is the one that I remember off by heart because I've just done it so many times. But you know, let's try and do it. Let's try and do it here. Right. Oh. HNO3. And nothing's gonna come here really unless it's gonna be a couple of electrons. NO2 plus. We're missing now a hydrogen and an oxygen, so H2O H plus. Oh, I don't know why that should happen there. Plus an electron. That's 2 hydrogens. An N. Yeah, 2 hydrogens, nitrogen, and 3 oxygens. That's fine. Yeah, so we're taking that, and then H2SO4 H plus plus HSO4 minus and why is it 2 electrons here? H2SO4 HH it must be, I mean, if I'm doing the ionic equation, it must not form HSO4. it must form something else. Right, I'm just gonna find the Ionic equation to this at the end. I don't usually do the Ionic equation for this. It mustn't form HSO4, it must form something else. If you're doing the Ionic equation, but I'm not gonna try and I'll get the answer at the very end. So if you want to get the answer to the Ionic equation for these two, I'll do that at the very end, and I'll sorry, if you want to get the Ionic equation for this, I'll get that at the very end so that people don't get confused. But for now, as I said before, if you know how to do that, do it. It is a better way of doing that. I just don't know what the product is for this. But the most important part is just knowing that HNO3 plus 2H2SO4 goes to form NO2 plus 2HSO4 minus plus H3O plus. And the balancing part out is very easy to do. You'll see that. But yes, as I said before, here I said that, remember I said before that this is a catalyst, right? And you don't have to show this, but just to show you that it is a catalyst, the H plus from H3O plus can be removed to react with HSO4 minus to reform H2SO4, and showing that it's a catalyst and water is also being released, right? Sorry about this here. I don't like to kind of lead you onto something and then tell you something wrong. So I want to make sure I get you the right answer at the end. I thought I could just do this off the top of my head immediately, but I will get the answer to you at the very end. All right, so now I'm going to do show you the actual mechanism for nitration, right? So you don't have to separate them out like this. I've just done it. I've just shown you it like this, but you honestly don't need to show this part here. You can actually just represent it like this. You don't have to show the plus and the minus, but I've shown it here, mostly because it's just from Seneca, but also it's a good way of showing you, if you're looking at it deeply, right, why. Because when you're looking at it, right, it looks like this, and then it just comes. It's still like this in the thing, but it's not completely it's not in the way you'd think. It's just that the balanced charge. It's not that the bonds are, all the bonds are there now. It's just that its overall charge is neutral, so you just represent it as NO2. And I'll show you here, right? So for the first one, we'll be going from showing the bond for the arrow going from the ring on benzene towards the electrophile, in this case the nitrogen, which it should be. The nitrogen is the one that has the positive charge here, and then the second one's for showing the 2/3 benzene ring, because now it's the intermediate, showing the intermediate with the half or 2/3, not half, 2/3 full benzene ring with the positive charge, and then another mark for showing the bond breaking from hydrogen or falling in to reform aromaticity, and then another mark for. That's 3 marks. So you probably got 2 marks for showing the arrow, and then the ring with the positive charge. So I mean, in total it should be 4 marks. That whole intermediate in itself, it being bonded together, should get you 4 marks. So this should be like a 4-mark question. So 1. This isn't part of the mechanism. I mean, this is technically part of it, but you don't have to know about that part. 1, 2, 3, 4. No, 1, 2, 3. But then the entire mechanism 4. Yeah. I'm going based off the mark scheme of what the mark scheme says. A mark there, a mark for the 2/3 ring, and the positive charge. A mark for the hydrogen or this bond breaking in to reform aromaticity, and then another mark for just showing this intermediate in general, in the right way. You know that you should always write the final answer. You should always write the final answer, but you don't actually, in the mark scheme, you never actually get marks for this here. Even though you always write it, it's never correct if you just leave it like that. But in the mark scheme, technically, you never get the mark for this, the final, the finished product. It's always for here, the arrows in the arrows that's breaking this bond here, the positive charge, the 2/3 ring, and then the final mark is for just showing the intermediate here. But yeah, but this is what you should get at the end. And I said before, I'll actually show you. So this is the reason why I don't say it's like everyone would think that there's nothing going on here, but as you see here, you're breaking this bond, right? And you're getting an O minus because there's only single bond between nitrogen and oxygen. It should be a double bond. So that's the oxygen will be negatively charged. Here there should be 5 bonds in regards to nitrogen. So it should be sorry, it should be 3 bonds. It's usually, I mean, it can form 5 bonds, but it should be 3 bonds, but it's got an extra bond. So that's why it'd be positively charged here. And that's why and if you see here, it's got positive charge here on the nitrogen, negative charge on the oxygen, and those would equally cancel each other out. So you can just write it as NO2, but it's actually technically a bit different there. But you don't need to know about all of that. I'm just showing you there just to show that I thought that may be a bit interesting, but I'll show you how I actually go through the mechanism myself to show you how you should write it and how you could write it. Because this part here is just to show you that little thing there, but really, how I look at it, if they ask me to do this, oh, this is how I do it. Here, NO2 plus. You don't have to always do the reversible arrow. I did it because technically it is actually a reversible reaction, or according to Seneca it is. In case someone teacher's gonna come out and say no, it's not, it's completely wrong, but they're usually quite right. But I in the exam you can just do a straight arrow. They won't penalize you for that usually, so you'll be fine there. Here, now 2/3 full ring, positive charge, hydrogen, NO2, that breaks, that bond here breaks. I don't like how close that is to the I don't like how close that was to the top there. There you go. I want to be from the center of the bond, just in case it's there's small things that this like right. Some examiners are very stingy if it's very obvious, but I don't like the arrow being close to the end here because I like it going from the center of the bond there, just to make sure that the examiners don't try and remove marks from me. But anyway, so yeah, so arrow going to the NO2 plus here to the electrophile. Make sure to the nitrogen, not to the O2, not to the center here, to the nitrogen specifically. That's where it's going to. Then it forms this intermediate here, bonded to NO2, but then it's a 2/3 full ring, positive charge, or it could be 3/4. It could be a 2/3 or 3/4. Anyway, in between, that's fine. Then you have to break this bond to maintain to reform aromaticity. You release a H plus in doing so, and you reform aromaticity here. And you don't have to show the H plus as far as I'm concerned, but that's maybe that's the reason why they don't give a mark for all of this here. But that's how you should represent it. It doesn't take long. They could probably get 4 marks, so you usually get a mark per minute. You could do that within 1 or 2 minutes, really, if I'm being honest. And yeah, so sorry, the camera kind of cut out there, but I'll kind of go on for what I was saying there. Yeah, so nitration has actually uses in industry. It's not just something that we just say for the sake of just saying it. It actually has uses in the industry. One of them is the nitration reaction. That's quite important, or Nobel. I think was it Nobel? It should have been Nobel that discovered it, hence Nobel Peace Prize. But TNT. I'm not talking about the Minecraft. I guess Minecraft one is the one that everyone really knows. But yeah, the nitration reaction is very important in the production of explosive TNT, 2,4,6 trinitro toluene. Nitration is also important in producing aromatic amines, which can be used for the synthesis of dyes. So you can use this dye if you use it for dyes as well. I think you can use it as cationic surfactants as well. There's a list of things that benzene is used for, but nitration specifically, dyes and for TNT. And how the TNT actually works? So toluene, I do believe it's the formation of 2,4,6 just forming the nitration reaction that's done to form 2,4,6 trinitro 2,4,6 toluene is actual process of explosion. Actually, because if I'm wrong, someone come at me and turn, but I do believe that's how it is. But toluene itself is just also known as methylbenzene. Methylbenzene is just toluene, right? the reason it's called 2,4,6 trinitro-toluene. That's what TNT stands for. Trinitro 2,4,6 toluene. It's called 2,4,6 because there's a nitro group, or there's a nitronium bonded to, or NO2 bonded to the second, fourth, and sixth carbon on benzene. The first one obviously is the methyl, but as we call it, toluene is just methyl benzene anyway. But yeah, this is the reaction. The nitration reaction here can happen, but if it's concentrated nitronium, so if it's concentrated nitric acid, you can then lead on to getting 2,4,6 trinitrobenzene. Now, I think it is explosive, but not the part that actually explodes. But I'm not gonna try and confuse too many people. But I know one thing I know for certain is that this is very explosive. This is very, very explosive. Yeah. So remember, this is bond forming is exothermic. I do know that. I think forming this bond in itself is quite an exothermic reaction. But anyway, all you need to is just pretty much all it is just the nitration reaction happening 3 times. So it happens once, twice, and a third time. I do believe that forming this in itself is enough for the explosion to happen, or it's what happens in the stage of explosion. But in case I'm wrong, and this itself doesn't explode by itself, all I know for certain is that this is an explosive compound. But anyway, I'm gonna stop waffling now and going for it. This is it. This is just this is a preparation of 2,4,6 trinitrophenol. So maybe it isn't the explosion part, but it is. Maybe it might not be the actual explosion part, but I know if this in itself is explosive, and it can be used. This can be used to then be ignited. I think maybe you have to ignite this to cause it to explode. So this is forming. I think this is forming TNT, and then you have to actually heat it again to explode it. But either way, the important part, you actually need to know about that part, about how it explodes and all that, or in terms that it can form TNT, which is explosive, and how it does it. It's just multiple rounds of nitration. The first one here, a second one, and a third one. And the reason why is because we have concentrated nitric acid. Anyway, I'm going to go on to the next part here, which is about Friedel-Crafts. So the last type of electrophilic substitution is the Friedel-Crafts acylation. Reason why is because there's 2 gentlemen whose surnames were Friedel and Crafts that discovered this, and it's just with an acyl group. It's just acylation with an acyl group. So Friedel-Crafts acylation can be alkylations and acylations. So I'll go through the acylations here, but it can be with alkylations. So acylation of benzene. So the acylation of benzene adds an acyl group, so RCl plus. Right? Remember what we did? I discussed what the acyl groups are in previous videos, but the last video definitely. The acylation of benzene adds an acyl group to the ring. The reaction involves the transformation of the acyl chloride. It's usually an acyl chloride, but it includes the acyl group in it, and you have to convert it into an electrophile or positive ion, cation, and therefore, it's cation. Cations are. Yeah, cations are the positive ions. Yeah. Mesyl cations. But you're forming the electrophile cation in this case. I don't like calling it. Either way, the acyl group here is acting as the electrophile. But you have to form this group because initially it's an acyl chloride. It's an acyl chloride, and you have to transform the acyl chloride into an electrophile using the AlCl3 catalyst. So what happens is, right, so the R here is just to represent how long the compound is, but let's say you had let's say this compound, let's say R was a methyl group, right? Let's say R was a methyl group, so here, and then you had this part here, your acyl group. The acyl group here is just this part, the COCl part. COCl. Sorry, the RCO. There you go. This part here, the RCO, that's the not the Cl part. Yeah, the RCO plus there, that's the actual acyl group, and then you have the Cl, usually being acyl chloride. So you have to, in order to actually make this an electrophile or positive charged, we need to remove this chloride here. That would be the easiest thing to do. You could remove the oxygen, but that's way too difficult. This is a very strong bond. The best way to do it is remove this chloride. How we do it is we react the acyl chloride with a catalyst which is called AlCl3 or aluminium trichloride, I think, and that forms RCl plus and AlCl4 minus. That's the first reaction with AlCl3. So this electrophile can then undergo the usual electrophilic substitution as seen below. Now I want you to actually do this. I want you to pause the video now, and I want you to actually try and attempt electrophilic substitution of this reaction. So pause the video now and actually attempt to do it, and I'll show you how to do it at the end. Right, so I'm going to assume that people have actually tried to attempt to do this, and it's as simple. It's the exact same mechanism, different compounds, but the exact same mechanism. Is there anything really extra to show here? No, there shouldn't be anything extra. All right, so the first thing, remember the very first thing is it's always from the electrons in the ring of benzene. Oh, I want. I had to make it a bit more of a blatant benzene arrow. So it's a curly arrow. That's how we represent electrons moving. It's a curly arrow. So yeah, but you guys already know that. From there to there, now we've done that, we formed the intermediate. I'm just talking for the sake of like trying to explain to you what's going on here, but in reality, I don't believe you should ever really spend more than a minute doing this little mechanism here, because it's really simple. It will save you time at the end of the exam to go and focus on other more important things, or if you need to review maybe some questions at the end some questions that you missed out on previous. So these mechanisms are always good because you always know you can save time with them. If you know how to do them, you can save a lot of time on them and take advantage of that. But yeah, that's it. So as I said before, arrow going from the ring to the nucleophile, the central carbon atom here, which is the one that's the positively charged there. That's the first mark. The second one is then forming the ring with the positive charge in the middle, the 2/3 full ring or 3/4, and then with the positive charge, and then the third mark is showing the bond breaking between the carbon and hydrogen here to form the to reform aromaticity, and then the fourth mark is actually forming this intermediate here. And then always do this. You don't get the mark for it, but you won't get a correct answer. They won't give you the full marks by actually showing that you've done this, right? It's not correct if you don't show the final outcome, but technically in the mark scheme they don't actually give you the mark for this. It's always the mark for what I've just said already. So yeah, but that's it then. There you go. Through the Kraft acylation mix. So above is now shows the mechanism for the acylation of benzene. First attack of the electrophile and electron dense benzene ring to form the positive non-aromatic intermediate. So this is a non-aromatic intermediate, and we're trying to break. The second proton is then removed, and that's done. So first of all, this is a non-aromatic intermediate here, and then to reform aromaticity, we need to break this bond here. I kind of stumbled. I remember trying to explain this here, and I kind of stumbled on my explanation. The actual answer is because that we have this Al. The reason why it all ties in back together. So the reason why this bond is broken is because now we have AlCl4 minus, right? But the AlCl3 is the catalyst here. It gets reformed. We're reforming AlCl3. So when we get this right, we have, remember I should write this here. H plus is removed from this here because remember we've reformed that. The reason why this is allowed to happen is because now we have AlCl4 minus. The H plus will be attracted to the AlCl4 minus. A chloride will be lost from AlCl4 minus to reform AlCl3, and then we form H plus HCl. So Cl is lost from AlCl4 and reacts with the H plus to form HCl, and AlCl3 is reformed, showing that the catalyst is regenerated. So yeah, this H plus is attracted to the AlCO4 minus. That's it. Hopefully this video, I mean, I'm going to show you the part after this where I'm talking about, I said I was going to show you the Ionic equations. Yes, I did say that. So, but for now, that's the end of this video. Hopefully you found it helpful. The part after this will be me showing you the Ionic equation part. And yes, so I've got the official mark scheme here, just to, so I originally thought it's going to be using the SO4 minus, but no, it's still forming the HSO4 intermediate, and it says here penalize equations that which produce SO4 minus, which is what I thought the HSO4 would be doing. But what I didn't think about here is that this is not a redox reaction. I think I was in my head, I was thinking about a redox reaction. No, it's just a half equation, but there's no electrons that needs to be involved in. So if I just kind of go, oh, right there, right? So the one that we did, the one I said, and the one I always do anyway, is this one here. Because that's the easiest one for me to remember. Really easy to do. But they do allow, they said allow this one here, which is between H2SO4 plus HNO3 plus NO2 plus goes from, sorry, H2SO4 plus HNO3 goes from NO2 plus H2SO4 minus plus H2O. And that's this one here is because of a redox reaction. So because of two half equations. I keep saying redox reaction. No, it's because of two half equations that have been put together to form this. I'm gonna just show you how it was. It's not a redox reaction. It's just an ionic equation that's made from two half equations. I'm just gonna show you here. So it's H2SO4. And if it's wrong, someone in the comments can just come and say you're wrong here completely. But this is the only way that I can see it happening really. H2SO4 goes to form HSO4 minus plus the H plus, right? Then you have, and that's pretty much balanced. That's balanced. HNO3 goes to form NO2 plus, as we said. But then we're left with one oxygen and one hydrogen, and that's not really how we balance. We usually use a water to balance. I mean, you can use an OH minus, but an OH minus to balance, but I'd first of all go for H2O, and that's left me with now a H plus on this side to balance this. And I have two hydrogens on this side, and only one on this side, so then I add the H plus here. Now the positive charges are now balanced, so now that's balanced entirely. And I can just put these two equations together. H2SO4, I can now put these two together. So H2SO4 plus HNO3. So H2SO4 plus, I can cancel these H pluses here and cancel out that H plus there because they're on the opposite sides. H2SO4 plus HNO3 goes to form HSO4 minus plus NO2 plus H2O, and that's what we have. H2SO4 plus HNO3 goes to form NO2 plus. So let me actually use a different color here to actually show you. So let me remove this little thing here. Right. Oh, that's wrong one there. H2SO4 plus HNO3 plus NO2 plus HSO4 minus plus H2O. And then we have the H pluses cancel out. And that's if you really struggle with this question, you can just do those two half equations first, and then add them together to make an overall ionic equation. But this one here is easy. I can do that one, but I'm not going to do it. Can I do it off the top of my head? Did I try to do it off the top of my head in the previous video? I probably did. Should I try? I'm not gonna. You know, it's really late right now. I'm not contemplating on whether. I'm just gonna leave it at that, so I don't confuse you. Should I do this one here? This one is correct in itself. Okay, then the top one will be the same. The top one would be the same. It's only going to be the bottom one that's really going to change, isn't it? Alright, cool. I'm going to try and attempt it. You know what? Why not? Why not? So HNO3 goes to form. I mean, we already know the products are going to be H3O plus, right? So NO2 plus H3O plus. That's 3 hydrogens here. So if I put like the oxygens are balanced out. 1, 2, 3. So 3 H pluses here. 2 here. So 3 H plus there. HNO3 and R2 plus H3. I'd have to add a negative charge to this side. It makes things a lot more complicated. All you need to know is that if you, I mean, this equation in itself, you just know it. You just know it. I mean, it's very, you know, it's NO2, an NO2 plus that's being formed, and HSO4 minus, and then you know, I mean, if you know the 3 ones that's getting formed, I just know this one off by memory. I'm not gonna try and do it and confuse it anymore. I'm not gonna try and confuse it anymore, so I'm gonna just neglect this one here. Object eraser. Neglect that one because I don't want to try and confuse it anymore. If you want to do half equation, then just do that one, which is the one below. But if this one here, just know that HNO3, H2SO4, NO2 plus, H3O plus, and HSO4 minus is involved. And then you can just balance the equation, which you should be able to do. Yeah, it's easy to know that a nitronium ion is involved. Easy to know that HSO4 minus is involved. And it's maybe this one you might forget, but you should be able to, if you do it enough times, then you'll be able to do that. That's it though. Hopefully this video is helpful, and that's the end.